Hello everybody, welcome to this video about u-substitution. Hooray! Okay, so what is u-substitution? U-substitution is a method of integration that helps us to see patterns maybe a little bit more easily than we might just by looking at the original problem. So we've actually done a lot of problems already that you can use u-substitution for, and some of you have been using u-substitution for them, but they're doable without them. So here's an example of a problem that you can use u-substitution for, but that we also know how to do without u-substitution. So if we were going to use u-substitution for this, what you do in u-substitution is you choose some expression that appears in the problem, so some part of the given problem, and you're going to let u stand for that. So usually if there's an inside function somewhere, that's going to be what you let u stand for. So here I'm going to let u equal x squared minus 7. And so then you rewrite the problem in terms of u instead of in terms of x. So that's going to take care of the x squared minus 7 underneath the radical. I still need to figure out how to take care of this dx because I need my new problem to be in terms of u, and so I'm going to need a du and not a dx. So what I'm going to do is, once I've decided what u should be equal to, I'm going to take the derivative. All right. And then I'm going to solve this for dx. I'm going to treat dx as if it can be multiplied over to the other side. And then x dx is equal to du over 2. So if you think about this problem, the original was like this. Okay, and what I have here is x squared, whoops, sorry, I wrote minus 5, this should be minus 7. This is u, and this is du. So I can rewrite this problem as square root of u times du, and I want to take the integral. When we change variables, we also have to change the bounds of integration. So this was 1 and 5. To figure out the new bounds of integration, you just plug the old bounds of integration into the expression for u. So when I plug in 5, I get 5 squared minus 7. So the new upper bound is going to be 18. Then to figure out the lower bound, you plug in the old lower bound, which was 1, into this expression for u, and you get 1 minus 7, which I think is going to be negative 6. We're going to have to, hang on one second. Yeah, the lower bound in the original problem is wrong. It should be 3, not 1. That's my bad. So then when we plug in 3, we get a lower bound of 2. Okay, there we go. So now we have this problem here. This is a pretty straightforward integration problem. When we integrate, so we can make this the integral from 2 to 18 of u to the 1/2. du. When we integrate that, we just use the reverse power rule. So we get u to the 3/2 times 2/3. So that's u to the 3/2 divided by 3/2, but then I just simplified. And then evaluated at 18 and 2. So you get 2 times 18 to the 3/2 all over 3. Minus 2 times 2 raised to the 3/2 all over 3. And if you punch that number in your calculator, I think you get 24 point something. The exact answer is on the next page. But so this expression here, u to the 1/2 du, that can be more easy to integrate. than the original given problem. So the advantage for u substitution is that you might be able to rewrite the given problem in a form that is easier to integrate and whose pattern you recognize a little bit more easily. We've gotten pretty good at being able to spot, oh, this is almost the, when we look at the original problem, this x out here is almost the derivative of the inside function. Just need to multiply inside and outside by 2, yada, yada, yada. So, but as we'll see in a second, there are problems where you have to do u substitution because you can't see the pattern immediately. This is a problem that can go either way. Okay, so here is the solution for what we just did. If you want to pause it and write in your notes, so this is the original problem. This is where we defined u. This is where we made a substitution for dx, so we had to replace dx. This is where we figured out the new bounds. And so this is the problem rewritten in terms of u. So here's the simplified version that we got to on the previous page, and then here's where we actually figure out the definite integral. Yay! So here I just did the problem without doing u substitution, so this is how we would have done this problem so far. I just popped a ×2 out here and a ×1/2 outside, and then reabsorbed the 2x because that's the derivative of the inside, added 1 to the exponent, yada yada. You get the exact same answer. So there really is no, so for me in this problem, it's easier to multiply inside and outside and not do u substitution. Some people see it differently. Some people did u substitution on the test and on some of the problem sets. If that makes it easier for you to see, go ahead and do it. You do need to be careful that you're doing it correctly and that you change the bounds of integration when you make the u substitution. There are a lot of multiple choice questions on the AP where we'll see one later on. So put a pin in that. Okay, so here's an indefinite integration problem, so we don't have to worry about any bounds. Let's go ahead and try to use u substitution to do it. So first I want you to figure out what you think u should be equal to. Then go ahead and rewrite this integral all in terms of u, and then we'll actually go ahead and do it. Okay, so here I will decide what u should be, and I think u should be equal to 5x squared plus 4. Okay, now take a second to rewrite this problem in terms of u. Okay, so here I've rewritten the problem. I started with my definition of u, and then I took the derivative. I got du dx equals 10x. I solved this for x dx because there's an x and a dx in the original problem. When I do that, I get that x dx is equal to du over 10. So when you substitute in, you get u cubed times du over 10, which just gets you to this problem. Okay, so go ahead and do the integration and then substitute back in for x. Okay, so over here in green, I went ahead and integrated. The antiderivative of u cubed is u to the 4th over 4. And then I have this 1/10 hang out here, so you just get u to the 4th over 40 plus c. And remember that u stood for 5x squared plus 4, so I plug that back in, and we get our final answer right here. Okay, moving on. Okay, so as I said before, u substitution also allows us to do some problems that we can't do without u substitution. So the previous games we've done so far, you can do u substitution, but you could also spot the pattern. Here, we are sort of up the creek without u substitution because the derivative of the inside of this function is just 2. But outside the function, we have an x. So we're off by a variable. That's going to be problematic for us. There's nothing we can do to integrate this without using u substitution. So go ahead and take a second, decide what you think u should be, and then go ahead and rewrite the integral in terms of u. Okay, so I let u be equal to 2x minus 1, what was inside the square root function. So that's going to let me take care of the 2x minus 1 here. So I've got this. This is going to be replaced by u. So now I have an x and a dx to take care of. So to figure out what dx should be in terms of u, I go ahead and take the derivative, like you did right here. You get du dx equals 2. When you solve that for dx, you get that dx is equal to du over 2. So this piece is going to be du over 2. Unlike the previous couple examples, we still have this x hanging out in front that we need to take care of. So what I did is I went back to what u is equal to, and I just solved it for x. So when you solve that for x, you get that x is equal to u plus 1 over 2. So I'm going to replace this x with u plus 1 over 2. And when you do that, you get this integration problem right here. Okay, so a simpler way to write that, I'm going to pull out a 1/4 in front, times the integral of u to the 1/2, sorry, that should be 2 to the 1/2. No fraction, I already pulled out that. Over 4. Okay, so take a second, go ahead and integrate this, and we'll see what happens. Okay, so first thing I did was distribute this u to the 1/2 to each of these two terms. I got u to the 3/2 plus u to the 1/2. Then you can just do reverse power rule on each of those. The 1/4 is still hanging out in front, and then when you integrate u to the 3/2, you get u to the 5/2 divided by 5/2, but that's the same thing as times 2/5. So that's where this first term came from. Then I integrated the second term, got u to the 3/2 over times 2/3. And then the last step, I just went back and plugged in what u stood for. So now we're back in terms of x. It seems crazy that, if you think about the problem we started off with, that the derivative of this whole mess simplifies to something as small as x times square root of 2x minus 1, and that's why we would never be able to spot this pattern without u-substitution. But if you go ahead and you check this by taking the derivative of what we got, you do find out that it simplifies to x times square root of 2x minus 1, which is kind of crazy. But yeah, so this is an example of a problem that is not doable unless you use u-substitution. So on multiple choice tests, multiple choice questions, you will usually be told what you should make u equal to. So here's an example. I'll put up a multiple choice question on PlayPosit that's similar to what you might see on the AP exam, and then we'll talk a little bit about it. So go ahead and first rewrite this in terms of u. Okay. So I used the substitution they told me to. I made u equal to 2x to the 1/2. To get dx, I took the derivative. Got 1/2 to x to the negative 1/2 times 2. 2's canceled. I got du dx equals 2x to the negative 1/2. And then I just solved for dx and got that dx is equal to du over 2x to the negative 1/2. And then I had to spot something. This 2x to the negative 1/2. Remember that u is equal to 2x to the positive 1/2, so 2x to the negative 1/2 is u to the negative 1. All right, so this piece right here, this equals u to the negative 1. So then dx is du over u to the negative 1, which is the same thing as u du. Having u to the negative 1 in the denominator, you can move the u up to the numerator. So then when we rewrite the original problem, we get 1 over u plus 1. So this piece is, from the original problem, 1 over root 2x plus 1. And then u du, this is the dx. I accidentally wrote dx twice in the original problem. Might be. The last thing we need to figure out are the new bounds of integration. So go ahead and take a second, try to figure out what the new bounds are. Remember, you get the bounds by plugging the original bounds into the substitution for u. So go ahead and take a second to figure those out. Okay, when you plug in 2, you get square root of 4, which is still 2, so the lower bound doesn't change. When you plug in the upper bound, you get 2 times 8 is 16. When you take the square root of that, you get 4. So this problem is equivalent to the original one. So in these types of problems, you're going to have to do the substitution and then make sure you spot the new bounds and then choose which option in the multiple choice corresponds to that. You don't actually have to solve this integral, and actually I'm not sure that we know how to actually compute this integral. You just have to be able to spot the new form once you use u-substitution. Okay, so there'll be some practice problems posted up on